So we've already discussed the fundamental theorem of calculus. Now let's discuss the second fundamental theorem of calculus. And I know that sounds kind of odd because why would you have the fundamental theorem and the second fundamental theorem? But these are very intertwined. They relate very well to each other. So in a lot of ways, depending on what sort of text you read, you'll hear it described as the first version and the second version of the fundamental theorem as opposed to being separate theorems. But anyway, we know that if f is integrable, so if it can be integrated on some ab, then this integral is just some number, right? It is some number, and specifically it has to be continuous on this. But anyway, but what about if I said a with b plus 1? Like, what if I wanted that interval to be larger? What if I wanted that interval to be slightly smaller by dividing by 2? Well, that'd be annoying, right? We'd have to generate the first integral, then the second integral, and whatnot, and generate all those numbers. So what if instead we thought of it as like a parameter? What if we said, let's fix a, but what if we set up that second endpoint as like a sliding value x that we can adjust? So we can represent this arbitrary upper bound with x. So we integrate from a to x of f of t dt. Now what that means is that we know this thing is going to be integrable, or rather we need to control whether or not it's integrable on that particular subinterval, right? You don't want to push x so far that the function becomes non-integrable, like if it goes through a discontinuity or something like that. But assuming you haven't done that, then that's really just a function of x, right? Because whatever I plug in here affects what goes in here, and then once this is just some fixed number, becomes just a standard integral because this is just some number. So this looks complicated as a formula, but ultimately it's just a function of x. And if you look at that, well, f of x is kind of like an antiderivative, right? Because we're going to produce an integral, or once we perform the integration, we end up with some sort of function, which turns out to be an antiderivative. And why is that important? Well, if it's an antiderivative, then when we take its derivative, we get back the original function, right? That's the definition of an antiderivative, is when I take the derivative of the antiderivative, they have that cancellation, and I get back my original function. That's important because now what I have is, instead of the antiderivative being some explicit polynomial or trigonometric function, I have it defined in terms of the original function. It's defined in terms of the original function. Why does that matter? Well, it matters because when I take the derivative here, I kick out the original function. And you might say to yourself, well, why does that matter? Well, the reason that matters is oftentimes you're going to have some sort of function that's really ugly, it's really hideous, and you may need to deal with the integral, you may need to deal with the derivative, you may need to deal with that stuff. And by doing this, you never actually have to compute what big F of x is. You can kind of juggle this and deal with it as necessary. But another reason that this is a neat way to represent this, is that you can think of it like an area accumulator. So if I start at A and I start sliding x, what I'm doing is I'm sort of gathering area, right? As x gets larger, I get more of this area. If I keep going, I get more and more area. Actually, and even if I go backwards, I get what you might think of as negative area. So your net change will be negative because I'm defining this as kind of positive. So if I'm going backward, that's sort of like I'm going in the negative direction, so I get a negative answer. But the idea is now you have this sort of sliding window where you can build up area or you can reduce area. And that's the idea here. And I will say, in practice, I don't use the second fundamental theorem of calculus very often. The first one, it's lights out. It's always used. But the second one, it doesn't come up as often, but it is a necessary, or rather a very interesting result. And when you need it, man, you're sure glad you have it. But Generally speaking, this is not applied nearly as often as the canonical fundamental theorem of calculus.